Hi guys, this is Dr. Edwards again. Now I'm going to present to you some concepts that differs from stationary states and go into the other main category of quantum mechanics, scattering from a single dimension potential. And so let me get started. Now, you'll find that the mathematics and the technique differ significantly from stationary states. With stationary states, we always wanted to get a normalizable wave function. And that means that we could talk about finding the density of state functions, for instance, and we could calculate the uncertainty aspects, the uncertainty in position, the uncertainty in the particle's momentum. Now, differently now, we won't necessarily be trying to find those quantities. What we're going to be looking for will be called the percent of transmission and the percent of reflection of the wave. So let me get started. Just as a way to recall, the general wave function that we will talk about will be of this kind. It's a wave function of both position and time, written in this manner, a e to the I kx, and this represents a traveling wave. This also represents a traveling wave, b e to the negative I kx, and the time aspect is in this portion here. So you see, this looks like what all of us should have seen. As a traveling wave, this is the position part of the wave aspect, the time, energy over h bar t, energy over h bar t here. This term represents a wave traveling to the right that has the negative sign there. This term represents a wave traveling to the left that has the negative sign there. And the energy of the particle is known, where the energy of the particles was not known for stationary states, but we were able to determine the energy from solving the Schrodinger equation. For these kinds of problems, the energy of the particles come in from infinity, say from the negative infinity. They encounter the potential and get scattered either through the potential or get reflected back from the potential. Let me get into it further what I'm talking about. But as we get into this, let me have you recall that if you have a differential equation of this form, d second psi dx second, with the plus sign there of some constant a squared, this represents a traveling wave. Now, if you just have a negative sign there as opposed to a positive, this is no longer a traveling wave. This is an exponential growth or decay. Psi will now be an exponential growth or a decay. It will not be a traveling wave. And you will meet both of these aspects in these scattering type problems. Also true for the kinds of problems that we're talking about here, that if the energy of the particle is less than the potential at negative and positive infinity, the particle is bound. And these are stationary state particles, well, the kind that we've been dealing with previously. But if the energy is greater than the potential at negative or positive infinity, one or both of these, then you have scattering state particles, so a scattering situation going on. Now, so I'm taking this from Quantum Demystified. I'm going to skip this portion here, but let me get in right here. Now, so this is the way the potential is going to look. So this is then potential on the vertical and position on the horizontal. Some region, the potential may be negative here, but then the potential may go up high, positive there, and stay constant for some distance x, and then it may be there. So we have these different situations going on for how the particle encounters a potential, if you will. Okay? Now, so we want to solve the Schrodinger equation in each region that we come upon. And some of the problems I give you initially, there'll be only one or two regencies, obviously so that the math will not be so very difficult as we get started. So if the particle are in an unbound region where its energy is greater than the potential, the wave function will be of this form. This is a freely traveling wave. All right, this form is okay. Now, if the energy of the particle is less than the potential energy, then you get a potential, get a wave function of this form. A e to the beta x plus or minus b e to the rho x. Okay? Now, this is not a traveling wave. Here is traveling because the I is there. The imaginary number I there makes both of these traveling waves. What else must be true about the wave function? That the wave function on the left side at some point must be equal to the wave function on the right side of the step, if you will. And also the first derivative on the left side of this step must be equal to the first derivative of the wave function on the right-hand side. All right, basic concept. Then, as I say, two of the things that we will want to calculate will be the transmission coefficient, which will be the ratio of the magnitude of the current density to the right divided by the incident current density. And the reflection coefficient is the magnitude of the reflection current density divided by the incident current density. And J here is what's called the current density. All right, let me go on. So let's then look at some particular problem here, and then we can get a better handle. So this is the way the Schrodinger equation is going to look. And we can now go on and define K here, Ki squared, as being equal to this term here, so that the equation looks less ominous. So here we have, so look at this example here. This is a particle now where the particle comes in and encounters this structure with its energy less than the height of the step. Classically, this particle should get totally reflected. Quantum mechanically, if the step is finite, some part of the probability the particle would get through. But if this step is infinite, it's still going to get totally reflected. So let's see the mathematics for this problem then. So here the incident wave is the following. This is the wave traveling to the right, as I say. And the incident plus the reflected wave, this is the wave traveling to the right. This is the wave that's traveling to the left. Okay? And so for x greater than 0, this is the Schrodinger equation that has to be solved. Written in author form is this one, is this. And now, here is now. So this goes back to that equation that I spoke to you about at the beginning. If you have a plus sign there, you will find that this is no longer a traveling wave, but it's going to be an exponential growth in this case, an exponential decay in this case. So this is the way the transmitted wave is going to be an exponential decay. So the wave comes in here, it strikes the potential, and it feels this exponential decay. So it is like it loses its potency. Its probability of getting farther into this region is decreasing as you get farther and farther into the region, if you will. All right. Now, so let me go on and get the final answer here. That using J, and you can go through all these steps, we get then that the reflection coefficient R is equal to J reflected divided by J incident, turns out to be equal to 1. So this 1 here represents 100%. 100% of the energy of the wave is reflected in this case because the step is infinite. Doesn't matter how much it decreases, all of the energy gets reflected back. And the transmission here is 0. In this next example here, the particle comes in now with energy greater than the step. In classical mechanics, all of the energy would get through. But you will find out here for this situation, some of the energy is reflected. And so we go through the steps here of solving the Schrodinger equation. And this is written out so that you can go through all of the steps. I'm going to give you the answer here. The transmission coefficient becomes equal to this expression here, 4k1, k2 over the quantity, magnitude k1 plus k2 squared. And the reflection coefficient is this. You should be able to add these two together and you always get 100%, okay? Finally then here, I go through a couple of examples here, back with example 3. The previous example. I look at some cases where, let's see, what do I do? This is the transmission coefficient. If I know the expression for K1 and K2, or know the energy, I can actually get a number for the transmission coefficient. Can be expressed in terms of the energy, and the reflection coefficient can be expressed in terms of the energy also. Now I look at a case here as an example. Suppose the particle comes in with energy 10 eV and the potential is 7 eV. How much of what is the of the transmission coefficient? I go through and I calculate 91.44% is the probability that the particle is going to get through this potential. But there is a small amount of 8.56% probability that the wave is going to get reflected by this potential. Although the energy, I say again, is higher than the value of the step, the mere fact that we're dealing with quantum mechanics give us the fact that some aspect of the wave is going to be reflected at this step here. Okay. Let me see, what else do I want to say here? I check a couple of different values, and so that you can compare. This is another example of a finite step, and we can go through the mathematics here as well. This one is a bit more difficult, but you can also calculate the transmission and reflection coefficient for this case as well. All right, that's what I wanted to share with you now. I want you to listen to my video many times and read through the mathematics in this section so that you will begin to get some appreciation for these scattering states now. And now you've been exposed to the other main aspect of quantum mechanics. You have the stationary states of the infinite square wave and the harmonic oscillator. And now you get the scattering from a one-dimension potential that becomes the other main part of quantum mechanics, okay? All right, that's what I wanted to share with you today. Have a good day.